Hey, AP Statistics. Today we're going to get into section 7.2. We're going to focus on sampling distributions for sample proportions. By the end of this section, you should be able to calculate the mean and standard deviation of the sampling distribution of a sample proportion p hat and interpret and I should say mean and standard deviation. Determine if the sampling distribution of p hat is approximately normal, and if appropriate, use a normal distribution to calculate probabilities involving p hat. So the sampling distribution of the sample proportion p hat describes the distribution of values taken by the sample proportion p hat in all possible samples of the same size from the same population. So if we wanted to know the proportion of people that we're going to vote a particular way, we could go out and get a sample of those individuals, and that proportion would change from sample to sample. And so if we did all those samples and plotted all those p hats, we would end up with a sampling distribution. So here's an example one, an approximate sampling distribution. Approximate because they only did 50 samples here, but so they got 50 p hats, but you could theoretically do many more. And this is the proportion of pennies from the 2000s. I can't quite remember when this book came out and when this sample might have been, this distribution might have been done, but we have 50 different samples of size 20, and we're looking at the proportion that had pennies from the 2000s. So we saw in one sample as high as 95% had that of those proportion of pennies were from the 2000s, beyond the 2000s, and then as little as looks like 35%, but usually around 60, 65%. That kind of seems to be the peak of the curve, and we can kind of see that shape, center, and spread, that whole distributions. But by the end of this section, you should be able to anticipate the shape, center, and variability of distributions like this one. It's not just we have to do it by a simulation or something like that, or collecting data. We could actually just know in advance where it's going to be centered, what the shape's going to be, what the spread's going to be, and calculate those things. So here's actually an example of some simulations of some sampling distributions for p hat. Notice that there are a couple of parameters that are changing. So p is one thing that's changing, the actual population proportion here. 10% of our population meets the condition here, 50%, here 90%. And so we can see how that might relate to the shape of the distribution in the center, where those distributions are, of course. And then another thing that we're playing with here is the sample size. So we have a sample size of 25. And now that's not how many dots were done here. That's every single dot, and we actually don't know how many were done, a lot. Every single sample was a sample of 25, and so we see the potential proportions there, 25, 25, and in this row we've got 100, 100, 100, and so we can see how the 100 kind of smooths thing out a little bit. There's more possibilities. This, by the way, proportions really does relate to a binomial distribution. If you just think about the number of successes and then divide that by how many there are, you got yourself a sample proportion. So you can think of it as 25 trials, 10% chance of success, and these are basically binomial probabilities. And then you just divide that, instead of talking about number of successes, divide by 25, and you've got yourself some sample proportions. So it relates to the binomial distribution. And one thing we kind of skipped over was how that shape, we see down here in these larger samples, appears to become normal. And even actually this one here, where we're centered at 0.5, seems to be fairly symmetric and maybe even approximately normal. So it's something we'll focus on. So first of all, shape. When n is small and p is small, so when the sample size is small and the proportion, the actual population proportion, is close to 0, the sampling distribution is skewed to the right. In terms of like the number of successes, 0 kind of gives us a wall. We can't go below 0, and so we end up with a skewed right distribution. It's possible you might get a decent amount, but usually it's pretty low, clustered down near 0, and so we end up with a skewed right distribution. If that sample size is low and our p is high, we end up clustered up here near 100%, and so we might get almost all of it, all of ours, if our sample size is small, that are successes, and we can't really curve out to the right there. So we kind of run into that wall, and we end up with a skewed left distribution. If we go, this is, let's see, this is the small picture here, or the wrong picture. When n is small and p is close to 0, let's see. Yeah, sorry. And this is the best situation. If we end up with a, so if the n is small and p is close to 0, the sampling distribution is skewed to the right. We saw that in the first slide there. If n is small and p hat is close to 1, the sampling distribution is skewed to the left. But if the sampling distribution becomes very close to normal when p is close to 0.5, so we're in the middle, and if n is larger, or both, and we saw kind of that in both of those cases. when we look back at that at all those together. So this is kind of our ideal situation: a large sample, and then actually if that p can be closer to 0.5, that creates the best situation. Then the center shifts, and it just matches whatever the population proportion here is. So if our population proportion is p is 0.1, see that this is centered at 0.1. And so on average, our sample proportions are centered there. Our mean of our sampling distribution is centered the same. That will be, if we go to 0.5, 0.9, that'll continue as well. So center is going to be centered at whatever the population proportion is, as long as we're using, unbiased sampling methods to get it. And then variability. So the variability, and we use these symbols, but I don't know if I've mentioned this, sigma sub p hat, the standard deviation of our p hats. And let me see here, I didn't mention it, but, and actually they don't mention it here, mu sub p hat, the average of our p hats is what the center of that distribution is. This would be mu sub p hat. But this is sigma sub p hat, so our standard deviation of our potential p hat proportions. It's kind of a weird symbol, something to make sure that you understand. It's different than just a sample standard deviation. It's a standard deviation for our sampling distribution. But that's what this number is. Sigma sub p hat depends on both n and p. For a specific sample size, the standard deviation of p hat is is larger for values of p close to 0.5. So this p was 0.1, that standard deviation is a little smaller, it gets a little bigger. We have kind of a little bit more variability when we have 50% chance than if we have only a 10% chance of success. So that's one thing. The closer we are to 0.5, the greater the variability is. But then the other thing that affects it is the sample size. So for the larger values, even though we're here at this center's at 0.5, it's worse than it is. Sorry, I guess I got ahead of myself here. So yeah, we see that the larger values of standard deviation close to 0.5 and so on. But if we go to a larger sample size, then we're going to have less variability. So even for the same p, for a 10% chance of success, or for p is our population parameters 10%. If we go from sample size 25 to 100, we see that standard deviation shrinks. So the bigger the sample, and that one's kind of one that you've probably always known, that, or at least for a long time have known, that that standard deviation shrinks. And in fact, there's a specific value that it goes by. If we multiply the sample size by 4, it cuts the standard deviation in half. So see, I don't know if you can notice here that 4 times the standard deviation, 4 times the sample size, that standard deviation does literally cut in half. And so that'll relate to our formula that we'll get to here. So, and then this is just kind of summarizing what I just said. The standard deviation gets smaller as n gets larger. So to summarize our sampling distribution, if we choose a simple random sample of size n from a population size big N with a population proportion of p successes, and let p hat be the sample proportion of successes, then, so we're getting a sample proportion from a large population, and if we're going to keep repeating those different sample proportions, the mean of that distribution is going to be equal to the population proportion. So our average p hat is going to match the population proportion if we're not biased. So that's the center is kind of simple. The standard deviation is a little less, and so here's our formula. The standard deviation of the sampling distribution of p hat is, and it's sigma sub p hat squared of, and then it's p times 1 minus p over n. And so you might look at that and think that kind of looks somewhat familiar. If you think back to the binomial distribution, this is actually very similar to the binomial distribution. The n, it used to be n times p times 1 minus p for the binomial distribution. Well, if you divide that whole thing by n and do some simplifying, bring the n inside the radical, you end up with this formula. And this does exactly what we want it to do, in the sense that when we plug in a bigger n, the standard deviation gets smaller. And then if this p is closer to 0.5, that standard deviation gets bigger. And the closer this p is to 0 or 1, it gets smaller. And so it behaves just like we would like it to. And we could kind of go back and look at how it relates to that binomial standard deviation. Now this does require, since it is kind of based on that binomial formula, it does require that independence. If as we're sampling, if we're taking individuals from a population that's pretty small, we can affect that probability. So this relates back to that 10% condition we covered with the binomial distribution. Since we are sampling, we do need our sample to be less than 10% of the population size. And in that case, then we can get this standard deviation, which measures the typical distance between our sample proportion and the actual population proportion. It's kind of our typical error, really, right, that our p-hats are off by. And then finally, the sampling distribution of p-hat is approximately normal. We actually get that normal shape as long as the large counts condition is satisfied. And so what we want to see, and it's kind of a combination of a larger sample is good, and then p should not be too close to 1 or 0, and so that's what both of these check for. N times p needs to be at least 10, and so that's actually the expected number of successes. If you remember from binomial, you need to have at least 10 of those, and then n times 1 minus p needs to be at least 10. That's the expected number of failures, and that needs to be at least 10, so that you actually have room for the curve to kind of curve out on those sides. If you get too smushed up against the max or the min, that's when you get the skew happening, which would be 100% or 0%. All right, so let's kind of put all that together and look at a sampling distribution for an example. Suppose that 84% of students at a large high school regularly use a backpack to carry their books from class to class. Imagine taking a simple random sample of 100 students and calculating p-hat, the proportion of students in the sample who regularly use a backpack. And so realize that when you do that, if you repeat that process, you're going to have variability. You're going to get different results. So what is the distribution of those results going to look like? So identify the mean of that sampling distribution of p-hat, and we're going to do some other things as well. So the mean, on average, our sample proportion should be 84%. Sometimes it'll be a little higher, sometimes it'll be a little lower, but on average, our sample proportion will average out to our population proportion, as long as we're not biased in our way of getting that, which a simple random sample avoids the bias. And then part B, calculate and interpret the standard deviation of the sampling distribution of p-hat and verify that the 10% condition is met. So we're going to do that square root of p times 1 minus p over n, but then we're also going to check and make sure, all right, does it seem like there's more than 10 times as many of that? Is our sample less than 10% of our population? And so they did say it's a large high school, so we'll assume that there's at least 1,000 students there. So assuming that n equals 100 students is less than 10% of the students in the large high school, so less than the high school needs to be at least 1,000. The standard deviation would be this square root of p 0.84 times 1 minus p 0.84 all over 100. And we do always p is plugged in as a decimal into our formulas. And so we get a standard deviation of 0.0367. If we want to interpret that, in sample random samples of size 100, the sample proportion of students who regularly use a backpack will typically vary by about 0.0367 from the true proportion of 0.84. So on average, our sample proportions will be 84%, but we're going to typically be off by about 3.6%. That's a typical amount of variability. It could be more, it could be less. That's like on average-ish. That's how far we are away from that population proportion. All right, and then finally describe the shape of the distribution. So we have the center is at 0.84. We have the spread 0.036. What's the shape going to be? Well, as long as we meet that condition of our n times p being at least 10 and n times 1 minus p being at least 10, which they both are. 84 is greater than 10. We expect 84 successes. We expect 16 failures. Those are both at least 10. So we actually expect that sampling distribution to be approximately normal. Not exactly, so be very careful to include that word approximately. That shape of that distribution is approximately normal. When using sample sizes large enough for n times p and n times 1 minus p to both be at least 10, if we check that large counts condition, the sampling distribution of p-hat is approximately normal. And so we see that kind of in this example here, where we have this really nice bell-shaped curve, and we can verify that it is actually very close to a normal curve. We can use the normal distribution to estimate probabilities based on that. We can do some normal CDFs and things like that. Another example, a polling organization asks a simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles from home, and then find the probability that the random sample of 1,500 students will give a result within 2 percentage points of the true value. So if we're dealing with a normal distribution, we can check is are conditions met. We can figure out what our mean and standard deviation is and do some normal CDF stuff with this. So first, They actually are kind of pre-drawing our distribution here, but our mean is going to be 0.35. It's, if we're doing a simple random sample, it shouldn't be biased in any way. So our average sample proportion will be that. Doesn't mean every single sample proportion will be that. Some will be higher, some will be lower, but that is our average sample proportion. And then assuming that there are at least 10 times as many as that from our population. So if we're talking first-year college students, there needs to be at least 15,000 of them, which we think we're good. So assuming that 1,500 is less than 10% of all first-year college students, we can use the square root of p, which is the 0.35 times 1 minus p, 0.65, all over n, and square root, and that's our new standard deviation. So on average, we're going to be centered at 0.35, but then we have our variability of 0.012, and that's our standard deviation setting this. And then finally, we check n times p and n1 times 1 minus p to see if they're both at least 10. They are by a long shot. And so the better we beat that condition by, the more approximately normal things will be. And so yeah, this distribution of p hats is approximately normal. So you see this normal curve over here. And so then we want to find the probability that we'll get the results within 2 percentage points. That means we want to be within 2 of this, so within 0.2. And so we can go from this plus or minus 0.2. And so we see that those, so really we're going from 0.37 down to 0.33. They turned those into z-scores to do this. You don't have to do this one. This way, you remember you could always type it in and they'll show this another way. But you could always type it in normal CDF with the actual raw values instead of converting to z-scores. But they're showing how you use the table with this. So z-score for 0.33, which is 1.63 standard deviations below the mean to 1.63 standard deviations above the mean. And if you do that, you could look up a couple of areas in the table and subtract to get that that's 89.68%. We could have also used technology doing with the z-scores, and this should say negative 1.36 to upper 1.36, so that mean standard deviation to get the same. And of course, we could type it in using the actual raw values, lower, upper, 0.33 to 0.37 with that mean and standard deviation. So under the right conditions, we can figure out that our sampling distribution of p-hat is going to be approximately normal. We can calculate the center, we can calculate the spread, and do some normal calculations with it.